Hello, welcome to One Class for the evening. My name is Fejiro, and I'm an honors Bachelor of Science student working currently towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and the college levels. If you need some extra homework help or just some further clarification, definitely check out the links in the description below. So, with that being said and the formalities aside, we can kick off this lesson with the first question for today, and that would be, what is the electron configuration of uranium? Okay. So, as I said, I like to just go, well, not as I said actually, I just treat this question as an individual question. So with this being said, we're going to actually look at the periodic table and locate uranium. So uranium, based on this, is right here. Okay, element number 92. Element 92. Okay, and let's list out what we know about uranium. So based on this, it's on row 7, and it's in the actinide series, which is just the elements after actinium. So now that we know those two, what I like to do to figure out the electron configuration is go through and count the in terms of like the whole configuration one by one, but I do usually prefer to use a shorthand notation. In this case, let's just go through it using the long-handed form. So starting from hydrogen, I just like counting through them, so through the elements. So we have hydrogen is 1s1, helium is the only exception, it'll be 1s2. So right now we have 1s2, okay? Then we tackle the next row, lithium and beryllium, okay? That would be your 2s2. Then we tackle the next part of the row starting from boron, and this will be your p shell from boron to neon. So it will be the second row, 2p6, and you follow that same trend for the third row as well. Sodium and magnesium will be 3s2, and then we have aluminum through argon, that's 3p6, okay? And then we have, for the fourth row, potassium to calcium is 4s2. But then we have all these in the middle here, which will actually count as your D subshell. So from scandium to zinc, actually, it will be 3D10. And don't worry, we will rearrange this later. We're just listing everything it has currently. And then, well, just to clarify where we have a 3 here, is that when you get to the middle part, the D subshell, you have to subtract -1 from whatever row you're on, okay? And then we go back to normal, so it'll be 4p6 from gallium to krypton. And then it keeps on going now, because remember, I have to get to the 7th row. We have 5s2. Oops, 5s2. Okay, and then we do the same exact thing where we subtract 1 for yttrium to cadmium, so it'll be 4d10 now. And then we get back to normal for indium through xenon, that's 5p6. Then we do the same thing for the 6th row, but it's a little bit different, okay? So for this, right, we actually have, if we look closely, the D shell starts with lanthanum, okay? It starts with lanthanum, so we have a 5d1, okay? Whoops, 5d1 for now, because we don't know what else we have. But then we have to actually address this lanthanum series, okay? So this lanthanum series will actually be your F shell, and there's 14 of them. This encompasses the whole lanthanum series. We have 4F14, okay? And then we get back to the D subshell from hafnium through mercury. And so you realize that instead of it just being 5d1, we actually have 5d okay, because that's from lanthanum to mercury. And now we have thallium through radon. That would still be now your 6p6. And then now we can finally go over to the seventh. Oops, sorry. We go over to the seventh row, francium radium. That would be 7s2. And then here's where it gets tricky. Actinium still counts as 1, as in it's 6d1. So it would have that, okay? But from actinium to uranium, since actinium is your 6d1, thorium is your 5f1. So we have 5f1, 5f2, and then 5f3 would be uranium, okay? So with that all being said, we're now going to reorganize this so that we have the answer that we want. So we still have the 1s2, 2s2, 2p6, 3s2, 3p6, and remember we had that d orbital 3d10, so it's 3d10. Then it'll be 4s2, 4p6. Same thing here, 4d10. But remember now we also have a f row as well, so we have 4f14, and then it keeps going. We have 5s2, 5p6, and we have a 5d10 here as well, d10, and then we have a 5f3, okay? Then we have a 6s2, 6p6, and then 6d1, and finally 7s2. That would be our reorganized structure. So that is what I'm thinking the answer is going to be. And in fact, what we could also do is do a shorthanded version. So I'm going to actually do the shorthand as well. So radon, okay, the reason why I picked that noble gas is because you're supposed to pick your noble gas for the shorthand notation, and it would actually encompass, I'm going to use the first example here, because radon would actually be all of this up until 6p6. That will be radon, okay? And then your new information is what happens post radon. So it'll be radon, and then it'll be same organization. I do believe it would be 5f1. Oops, not 5f1. Based on this, it's 5f3. Okay. 6d1. 7s2. So that's a pretty messy orbital, but let's see how we did here. Following the uranium, okay, interesting. It will have electron configuration as shown below. So it's, yep, 6p6, so at least we got that far. But I guess, oh, I see now what they did. So this is also a good learning situation here. What they do for the lanthanum and actinium series is that it looks like, well, actually from based on what I'm seeing here, the F shell gets filled first. As in, we don't have this awkward 6d1 here. It would actually just be 5f4. The reason why I thought it would be just the awkward one is because if you actually count from lanthanum all the way to lutetium, there's actually 15 elements instead of 14. So that last 15th element, that would be your d orbital again. So if you think about this, if we went from lanthanum all the way to ytterbium, technically it would be 4f14, and if it included lutetium, it'd be 4f14 5d1. Okay, so for this we're talking about uranium, which is back here, so it'll just be 4, it'll be 5f4 for this, not including that d subshell. So good to know. So it'll be 5f4, 7s2, and we can actually now fix that as well to reflect it. So we still have 7s2 here, we still have 5f4 there, Yep, 5F4 here. This will be gone. So actually, I'm just gonna move this 5F4. So based on what they're saying, and also they have a little diagram here, is that all the F orbitals prefer to be filled before you even, like the 5F, just like the 4F, before you even touch the d orbitals, the F orbitals are filled first. Hence why we have the off-bulb process. So this process right here, where we have 1s, 2s, 3s, 4s, 5s, 6s, 7s, and then we have 2p, 3p, 4p, 5p, 6p, 7p. Then we have 3d, 4d, 5d, 6d, and then we have 4f, 5f. So that's what they mean, as in, like, when I was going through this is the order that the shells would fill up in. So essentially what it's saying is that before you even touch your 3s, you have to make sure that your 2p orbitals are filled. Before you even touch your 4p orbitals, you have to make sure that your 3d orbitals are filled. And we're back. Okay, so sorry about that. We want to now see what is the molecular formula for butane. Okay, so what we have here, okay, is that butane, if we want to be able to name it properly, we have to actually look at what it's composed of. We have BUT of a prefix and ANE as the ending, okay? So what information does that give? Unfortunately, these are the things you kind of have to memorize, but so BUT, okay, if you remember, METH, that's 1, ETH is 2, PRO, P is 3, BUT is 4. Now all these are just in reference in the terms of the number of carbons, okay? PENT is 5. So each one has, there's 1, 2, 3, 4, 5, and it goes so forth. Like you have hexane for 6, and it keeps going like that. So what this is saying, okay, so this is the number of carbons. What this is saying is that butane has 4 carbons, okay? So now what does the A and E part imply there, okay? This actually, so just as how we have all of these listing down for numbers, A and E for the suffix means that it's completely saturated, okay? ENE means that there is a double bond present, and YNE means that there's a triple bond present, okay? Now the reason why this is important to know is because that way you know which formula to apply, okay? And for this one we're only talking about butane, okay? So because it's the A and E ending, that means it's completely saturated, aka you only have, so only single bonds, okay? That's what I mean by completely saturated. There is a specific formula for you to use to find out the number of hydrogens you have attached to your carbon based on the fact that it's completely saturated, aka only single bonds, okay? And the way you do this, right, is that, so you have your CN, that's your, you don't know your number of carbons, but it would be H. For completely saturated, it would be 2N plus a ring. So what I mean by branches and rings in terms of saturation, you'd be actually able to see that the branched part doesn't really matter as much as the whole ring part. You see that in later examples. But for butane specifically, when you draw it out, right, you have 4 carbons. So 1, 2, 3, 4. So carbons are here. And now, based on how many, I guess, the fact that it's single bonded to every other carbon, we can attach the hydrogens, enough hydrogens to where it completes its octet rule. So this one needs, because remember each bond shares 2 electrons, so this one needs 3 more bonds, so that's 3 hydrogens around it. Okay, this one just needs 2 more, 2 more, and 3 more bonds. So if you count it, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it even checks out here as well, which is why the molecular formula for butane is C4H10. Alright, so now let's move on to question 3. What is for the titration of HCl plus NH3? Chemical equation for HCl plus NH3. Okay. So for this, I like to just write this out by half reactions, then putting them together and then canceling out like the repeating elements. So HCl, as we know, it is a strong acid, but more importantly, the way it would react is that it will go from HCl, okay, and it will react with the water there, okay, and it will turn into Cl minus plus H3O plus. Okay, so that would be one of them. And now NH3, so it's able to take a proton or receive a proton from somewhere else, making it a base, because bases receive protons and acids give protons. So we have now this plus that H3O plus, and it'll turn into NH4 plus, which is actually what it does. It will look like this, you know, and it'll be a positive because right now it's neutral and hydrogen is adding a positive charge, okay, plus H2O. Okay, now I've written it like this. I specifically chose that because now, as you can see, you can actually cancel out certain elements. Okay, we have H2O gone, H2O gone, and H3O, H3O. Okay, so now what we have here is that, actually, let me see here. Interesting. I do believe we've done that. So we have HCl, okay, plus NH3 turns into, what's left is Cl minus plus NH4 plus. And now what they've done is that, okay, I see what they've done now. So for this case, what they've done is that they treated the HCl reaction as a separate ionization step, like dissociation step, and then those hydrogen ions are what's reacting. So in a sense, what they've done is that they have HCl just by itself dissociates to H plus and Cl minus, and then what they did there is that they did H plus plus Cl minus plus NH3 turns into NH4 plus NH4 plus actually just NH4, but actually this is very viable, but I think what we start to learn later is that they're actually hydronium, not just like protons technically floating in the water, if that makes sense when you're dealing with the acid. So I would actually kind of do a mixture of both. So instead what we have is that we're still going to use this here, because that's what it dissociates into, at least in water. So we have now all these H3O plus Cl minus, okay, plus NH3, okay, turns into, because this is now it's going to be a weak base, so we don't know if how much of the reaction actually goes through. But point being is that we'll now have H2O liquid plus Cl minus, still because it doesn't do anything, plus NH4 plus. Okay, so with that being said, though, we still have the spectator ions, the chlorine, so that one we can definitely still cancel out. But now what I have is H3O plus NH3 turns into H2O plus NH4 plus. So we still end up getting like the same quote unquote answer. This one only has NH4. This one I'm including the H3O because of the fact that, as I said, typically when you start working with acid and bases, you start seeing that it's actually hydronium ions rather than just a proton floating in the water. For example, when we look at this sheet here, instead of it just being H2O, we have a hydronium ion, and that's usually what you use to calculate your acid. So with this, I would still say both forms are correct. This is one is treating the acid as just a proton, which is how they have that formula, and this one I'm treating the acid as the hydronium ion itself. Okay, so this is correct. Let's move on to the next question now. Question number 4. Okay, what is the hybridization in CO2? So let's just write that out. Hybridization in CO2. So first we need to I guess draw out the Lewis structure for CO2. For this, I'd like to just refer to the periodic table to figure out how many electrons each gives. So either we can just see on the periodic table that carbon is the 14th column and oxygen the 16th column, but I like to do is still emphasize, just so we can get really familiar with it, the electron configuration. So this one we're only going over to the second row. So if we did the off-ball principle, so we have the 1s, 2s, 2p, right? Because it only goes to the second row. This would be how we would theoretically do that. So we first fill out the 1s part. So carbon will be 1s2, and then be followed by 2s2 and 2p, and if you count, 2. So looking at the valence electrons, just ones attached to the second, I guess, coefficient, which is these ones right here. You'll see there's only 4 in total, because 2 and 2. So carbon can give out, well, not give out, has 4 electrons. Oxygen, using that same steps, will be 1s2, 2s2, 2p4, based on where it is on the periodic table. So same thing. So oxygen can give out, well, not give out, but has 6 electrons. Multiply that by 2, you have 12 plus 4, that's 16 electrons total. Okay, so now ready to draw out the Lewis structure. We have C in the middle, we have at least one single bond, and then we have the oxygens. Okay, so now these carbon here in the middle is sharing 2 of its 4 electrons, so it still needs 5 and 6, and oxygen is sharing 1 of its 6 electrons, so it still needs 2, 3, 4, 5, 6, and the same thing here, 2, 3, 4, 5, 6. Okay, so now if you notice, we have these 2 single bonds here. I mean, not single electrons that can actually bond like that to form a second bond, or actually better if I drew it like this. There we go. These two here would move over to form a second bond here, and these two here move over here to form a second bond there as well. So in total, what would you have? It would be the same carbon, okay, the first bond on each side, and then the oxygen, but those electrons are now these ones here, okay. And with that being said, oxygen would still have its 4 electrons out there, and this will be the structure of CO2. So to figure out its hybridization here, the way that would work is that well, actually first you also want to make sure that you have the right bonding by using the electron number real quick. So for carbon, remember it has 4 electrons, so you have to subtract now the number of electrons it has as alone, which is 0, plus the number of electrons it's sharing divided by 2, and that does indeed equal 0, so it's perfect. And oxygen is 6 minus the number of electrons it has by itself, which as you can see is 4, and it's also sharing 4 electrons. So with that, this also checks out. So this would be right here the structure of CO2. Now to find out its hybridization, okay, you have to count how many things are bonded to carbon. We have 1 double bond here and 2 double bond here. But in a sense, because it's only 2 things, whether it's double, single, or even triple, it still counts as 2, okay? So it has the hybridization level of 2. And when you have a hybridization level of 2, okay, you are sp hybridized. Okay, so that right here is what carbon is in CO2. Okay, in fact, I'll specify that here for carbon. For the oxygen, okay, if you actually count it as well, you see it has 1, 2, 3. So for oxygen, okay, it has a hybridization number of 3. And when you do that, you just add another p orbital, so it would be sp2 hybridized for O2. Well, for oxygen. Okay. For oxygen. Let's see how we did. So, in the carbon dioxide molecule, carbon has an sp hybridization, perfect, and oxygen has sp2. Awesome. And exactly, they have 2 pairs of double bond, which is why it has the hybridization level of 2. And so that is why we can say that it's sp. And oxygen have 3 because of the fact that it has 2 lone pairs, which counts, and then it has 1 double bond. So that's still 3 in total, hence why it's sp2. And if you're probably guessing, if you were 4, so if you're like CH4 for example, okay, like that would be sp3 hybridized, because the hybridization level 4 is you have your s and then you have your 3 p orbitals. Okay, so this is correct. Let's move on to the next question. Question number 5. Okay. Assume the following decrease in order. Okay. What is the correct arrangement? Assume the following in decrease in order. Okay. Correct arrangement of Ga, Br, and krypton in terms of their electron affinities. So first thing, so arrange based on decreasing order. Okay. So electron affinity, which means its likelihood to, let me just make sure I'm drawing this right, something like that. That would be the periodic table. Alright. When referred to electron affinity, that is how much it likes to hold its electrons. And you will notice that the way it works is that if you go to the periodic table, actually let me just first copy this, because we'll definitely need multiple versions of the periodic table. So this right here, okay, is for electron affinity. That trend, all right, on the periodic table goes like this. Why? Because you notice that as you go more up and more to the right, these electrons here have an increasing amount of protons. I mean, not electrons. These elements here have an increased amount of protons, right? Which makes it have a stronger pull of its electrons. And another thing is that as you go up, you have less shells to deal with, meaning that the interaction between your nucleus, which is where the protons are, and the surrounding electrons are much stronger. Okay, so that's why it goes to the right and up like that. So the more right and up it is, the higher the electron affinity. So with that being said, let's look at the periodic table. The ones we have here are gallium, bromine, and krypton. Okay, so we have bromine here, we have gallium here, and krypton here. So from decreasing order, krypton is literally a noble gas. So krypton is going to just really shut down any, I guess, effort of them trying to take their electrons, because it's full. Or maybe, actually, yeah, that should be the case. Noble gas or not, just trying to make sure I have the right information here. Because, yeah, 7. Yeah, you know what? I'm going to go with what I understand. So with that being said, I do believe the order would be for A, start with krypton, then bromine, then gallium. Okay, let's see how we did there briefly. So what they say is okay, I see. So for this, the noble gas does affect it in terms of electron affinity. So if we were to kind of like electron affinity, yeah, it still go like this for the trend, although some do break it. So let's just actually highlight this part and say noble gases are like the worst ones in terms of electron affinity, because of the fact that their shell is already full, so they have no reason to accept another electron. Okay, and that's what they mean by that. Okay, so with that being said, though, back to this question then, because noble gases are automatically placed last, it's still that trend overall. So we have bromine that's going to be first, okay, as the highest. Then it's going to be followed by the gallium, okay, and then we have krypton last. A lot of well, it is a 53rd element, meaning that it has 53 protons. Rubidium, on the other hand, is a 37th element, meaning it has 37 protons. So that means the shells for rubidium are going to be kind of just more spaced out, because there's less of a pull towards the center. Okay, so with that being said, for B, if we were comparing strontium, barium, beryllium, calcium, and magnesium, which is all here, strontium, barium, magnesium, calcium, and beryllium was the last one. Okay, so all of these here, based on these, okay, since the size is increasing downwards and to the right, the biggest atomic radii, all right, will be the barium, followed by the strontium, then calcium, then magnesium, then beryllium. Reason being is because in this case, all we're doing is just taking off a shell each time we go up. All right, and now, same with atomic radii, but now we have Be, Bc, NOF, Ne, and lithium in terms of atomic radii. So pretty much this whole second row. So as you probably guessed, neon would have the smallest atomic radii, because of the fact that, so this is not an exception to noble gases, it is going to still be neon, because neon still has one more proton than fluorine and one more electron. So their pull overall is still going to make it as close as possible. Let me just go backwards from there. So neon is going to be the smallest one. So that means we actually have lithium, then beryllium, then boron, then carbon, then nitrogen, oxygen, fluorine, and neon is going to be the smallest one. Okay, that's the decreasing order for that. And now we have, what is the correct arrangement of this in the first ionization energies? So this is going to be the energy it takes for them to give up their I guess first electron. And with that, the cool thing is that ionization energy actually follows the same trend as electron affinity, because electron affinity says how hard it is to get rid of an electron, and ionization energy says, electron affinity says how much they love electrons, and ionization energy, so IE, okay, is saying how much energy it would take to get rid of an electron. So if you love electrons a lot, it would also make sense that you'd want to keep them, so you would need more energy to get rid of them. And we're still gonna just, I guess, air out the noble gases, because those ones follow their own trends really in terms of that ionization energy as well. So with that being said, let's look at sodium, lithium, rubidium, and krypton. Okay, so we have, potassium, sorry. So we have sodium, rubidium, lithium, and potassium. Those are the four. So sodium, lithium, rubidium, and potassium. So just these ones here. So based on this arrow here, okay, from least to greatest, all right, the greatest to least would be going downwards, because lithium would be the highest electron affinity in this case, and then followed by potassium. Oops, sorry, skipped one. Sodium, then potassium, then rubidium. Okay, that would be their the energy it takes to get rid of the first electron. It'd be kind of like that. And now number 5 is asking still for the ionization energy, but now we're going in terms of a column. Instead of a column, we're actually now going approaching in terms of a row. So we have now potassium, calcium, then gallium, germanium, arsenic, selenium, bromine, and then krypton. Okay, so like I said, krypton, I'm going to assume that for this ionization energy, it actually wants to although it's full, so it doesn't have any electron affinity really, to get rid of a electron would be pretty tough, because it wants to stay full. I think that's a key thing here. So ionization energy, you will still have, I believe, noble gases as the strongest ones, because of the fact that you really need to work hard to be able to ionize, quote unquote, get rid of an electron for krypton. So we have krypton is going to be the strongest, then bromine, then selenium, then arsenic, then germanium, then gallium, then calcium, then potassium. That is what I believe for that one. So just check it. It was quite an extensive question. The first part definitely threw me for a loop. Let's see how we did. Knowing that we can answer number 1, we have bromine, gallium, krypton. Perfect. So the reason why they said that is because, as I said, krypton is a full shell electron in terms of their valence shell, so it has no reason to have an affinity to electrons, because it's like, I don't need any more electrons. So we disregard the noble gas there. That'll be automatically be our weakest one. So that's why it's at the end, just like the answer. And then bromine needs just one more electron to fill its shell. So it's going to be like, I really want it. And gallium needs a few more here and there, but it still needs electrons to fill its shell, which is why it's stronger than the noble gas, but weaker than bromine. So now for 2 and 3, let's see how we did. Yep, barium, strontium, calcium, magnesium, beryllium. Perfect, because we did just follow our atomic radius sheet, so that's good. Number 3, same thing. We just followed the atomic radius sheet. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And now the ionization energy. So, like I said, the energy it will take to get rid of the electron, which is a little bit different than electron affinity, I believe. We should still have the noble gas as one of the strongest one if it's included. Let's see how we did. We have lithium, sodium, potassium, and rubidium. Perfect, because it does indeed follow this trend for ionization energy. Okay, so they're the same group. So exactly the effects of the valence electrons. Lithium is the smallest one, which is what's going to have the highest ionization energy. It's going to be pretty hard to get rid of that electron considering how close it is to the center of the nucleus. But for rubidium, it's quite bigger. It's like has 3 more subshells. 3 more shells, which is why it's going to be quite easy to just kind of pluck that one electron out of its outer shell. So now for the last one, let's see. Yes, we have krypton, bromine. Oh, I see. So arsenic and selenium are actually switched, but germanium, gallium, calcium, and potassium are good. So valence electron combinations. Half-filled orbitals are more stable than orbitals filled by other ratios. Okay, so the reason actually, if we go back to the periodic table, so this question actually showed, which I should have done because I have been trying to, all the importance of the electron configuration. If you compare selenium, okay, which is right, let me just make sure I have it correctly, Se, there we go, right here, okay, versus arsenic. So it's actually, if we go back to this, just making sure here, arsenic here has, if we wrote down its full valence shell starting from argon, okay, as an example, it'd be 4s2 3d10 4p3, and selenium would be same with argon, but 4s2 3d10 4p4. And what they're saying here is that a half-filled orbital, okay, so this is selenium, this is arsenic, okay, oops, sorry, I have it backwards, this is arsenic, this is selenium here, is that a half-filled orbital is more stable than a part way, because for 4p3 it looks like this is what they mean by half filled, just one electron in each p orbital. And then for selenium it looks like that, where now it has 2 electrons in one and the one in the rest of them. What it's saying here is that because it has 1 electron in each orbital, these electrons here are more stable, hence trying to destabilize them would actually be tougher. That is what this question is saying here. So for selenium, it wouldn't be too hard to pluck out this electron here, okay, because it's the odd one out. But for arsenic, it's done a good job of stabilizing each of its subshell with at least 1 electron, meaning that it's going to be quite hard to convince arsenic to get rid of that electron. So that is why the ionization energy is going to be high there as well. The reason why this doesn't beat bromine though, which is like this, okay, because bromine so desperately just wants one more electron that it's really just like, I'm gonna fight really hard to get rid of an electron, which is why that although this is technically more stable than like the partly filled shells, it still can't beat an element that's this close to filling its shell. And exactly, krypton is now completely filled, so it's like I have no business. Like, I am not going to give this because I am actually a perfect octet rule and everything. Like, I'm perfectly satisfied. I really don't want to give this up, which is why krypton is going to be the highest. So with that all being said, these two will switch. So because arsenic is partly filled, well, half filled specifically, half filled exactly, and selenium isn't, that's why we have this order here. So with that being said, this is kind of like a rule that you may just have to memorize, because there are a little bit of exceptions here and there. So that is what we have here. So with that being said, this is correct. And the reason why I say memorize this still is because you would think half filled is just more stable than like any other partly filled one, but as you can see here in this answer, even bromine is still stronger than arsenic, because even though it's partly filled, it's so close to having a full shell that's going to fight pretty hard to get rid of an electron. Fight pretty hard against getting rid of an electron. So now let's go to number 6 here. Molar mass of copper 2 sulfate. So molar mass of copper 2 sulfate. Okay, so for this actually we gotta first figure out what it means to have copper 2 sulfate to actually find the molar mass. We start actually with the sulfate, because unfortunately this is one of the ions you have to memorize, but you see it's an SULF, so sulf, which is sulfur, and the 8 means that it has a certain amount of oxygens bonded, so that'll be SO4. Okay, that is what it has for 8, and it's actually going to be 2 minus. Okay, that is a sulfate ion. Okay, and the way we can figure this out is just by checking the electronegativity number, or I mean not that, the electron number here in regards to sulfur liking to have specifically 6, and oxygen is 2. Sorry, I'm gonna put it here, down here, 6 and 2, and there's 4 oxygens, meaning there's an 8, and there's only 1 sulfur, 6, and because we have a negative, the oxygen here is serving as like that negative ion. So in terms of the ion number, we actually do get the 2 minus, because we have a plus 6 and minus 8, and that's how I personally know that it's sulf 8, because it fills in and checks out like that. If that helps you, that's great. If not, and you just want to memorize, you can go for that as well. I just like double checking that I have the right name. With that being said, we have sulfate and copper 2. This is definitely just going to be a copper, right? But this 2 right here is because if you look at it, copper is a transition metal, and transition metals can have different levels of ionization. Like, it can choose to give out 1 electron or 2 or however many, and what the 2 means is how many electrons it's given. So copper 2 is just Cu2+. So conveniently, we have a 2+ and a 2-, so no need to balance it out more. So copper 2 sulfate is just CuSO4. This is copper 2 sulfate. And now that we have that, we can actually do the easier part of finding the molar mass, which would be adding the constituents. So we have 1 copper, 1 sulfate, 1 sulfur, and 4 oxygens. Okay, so that's 63.546. Alright, and we have sulfur is 32.06, oxygen is 15.999, and so after multiplying we get 632.06, 15.999 times 4, 63.996 plus 32.06, and our total here, so the molar mass is 159.602 grams per mole, and I found that out by first finding out the formula for copper 2 sulfate, and then I added the atomic mass units of each of its parts. So with that, that should be the answer here as well, 159.607. They got a slightly different answer because, as you can see here, their sulfur is 32.065 instead of 0.06. So they are using a slightly different periodic table, which is fine, as long as the answer stays really close to your answer. Then you know you're doing it right. And by really close, I mean like there should be no more than like 0.01 difference about. It should be quite small to make sure that you are adding the right numbers together. With that being said, let's move on to question 7 here. Okay. How many atoms are present in 123 grams of magnesium cyanide? So, atoms present in 123 grams of magnesium cyanide. So for this one, you also kind of have to go step by step, starting with finding out what exactly magnesium cyanide is. So we know that magnesium is going to be just magnesium 2+, and cyanide is something unfortunately you have to remember, but it has a cyanide. Okay, so I like to remember this by just thinking of it as the CYA, Cia, is a carbon part, and nide is the nitrogen part. And this ion here is actually an anion. Okay, so when you mix these two, you have to actually double this to get net charge of 0. So we have 2 negatives and 2 positives. So magnesium cyanide is MgCN2, like that. Okay, so now with that being said, we have to find the molar mass, kind of like how we did in the previous question. So that's 1 times magnesium, okay, and then the 2 is going to be multiplied both to the carbon and the nitrogen. So it's going to be 2 times carbon and 2 times nitrogen, and so what we get, 14.007, 12.011, and magnesium, that one I do not have memorized, but that one would be 24.305. Okay, and now what we get is same number here because multiplied by 1, and carbon times 2 is 24.022, nitrogen times 2 is 28.014. So let's add it up. 28.014 plus 24.022 plus 24.305, and we get 76.341 grams per mole. So to find out how many moles are present, because that's the only way to find out the atoms, we'd have to convert. So with that being said, we have 123 grams as what we start with, and now we're trying to get from grams to moles. So we have to put the grams in the denominator, so it'll be 76.341 grams per is equal to 1 mole of what we're looking for. So with that being said, we divide 123 by that answer we got, the 76.341, and we get that we have around 1.61 moles of the magnesium cyanide. And now to find the atoms present, we have to convert from moles to particles, and we use Avogadro's number. There's 6.022 times 10 to the 23rd particles per mole. So the same way, we have 1.611 times, moles, okay, and then we multiply, and based on this, the moles are at the denominator, and we have 6.022 times 10 to the 23rd. Multiply those together, okay, and we actually get that there is 9.7. Let me see if we need significant digits. How much did we start with? 123. So 9.70 particles of MgCN2. Oh, sorry about that. I almost forgot. 9.70 times 10 to the 23. It's quite a huge amount. It's not just 9.7. Sorry about that. Particles of that. So that's what we get there. Okay. And that is exactly it. 9.7 times 10 to the 23. So this is correct again. And with that, let's move on to the next question, and possibly last question for tonight. We have draw the valence shell representation of a helium atom and sulfur atom. So valence shell of helium and sulfur. Okay. So for this time we're going to use electron configuration to figure out the valence shell. You can also just look at the periodic table and figure out from there. But electron configurations are just a more surefire way. So helium, starting there, okay. Alright, is that its electron configuration, if you see from periodic table, it will be 2s2, okay. And sulfur, right, it would start exactly, whoops, why did I put 2s2? 1s2, because it's in the first row and it's just a 2 filled there. Okay, sulfur would be 1s2, 2s2, 2p6, because we're still going and we're still basing up in terms of like solving like that. The next thing would be 3s2, and then we have 3p4. So remember, the valence shell is going to be the most outer shell. That's not coefficient. The coefficient determines what shell it's in, but the exponent determines how many we have. So we have 1s2. So in the first shell, which is the outer shell for helium, we have 2 electrons. For sulfur, we look at just the third. That's the coefficient there. That's the highest one. So we have 2 and 4. So sulfur will have 6 valence electrons, and helium will have only 2. So if we were to draw it out, okay, it would look kind of, you know, we have the helium nucleus and stuff, or nucleus plus every other shell in there, and its outer shell will look something like this, or more specifically, sorry, it'll look kind of like that, because if we were to draw the electron configuration for helium, 1s2 would just fill up like, whoops, 1s2 would just fill up like that. That'd be 1s2. Sulfur, on the other hand, would fill up, because this is going to be the S1s, and for sulfur, we're looking at the outside one, that's 3s, and there's 3, I guess, subshells for the p shell, which is why it can fit 6 electrons. So sulfur will look like this: together, separate, because 3p4. In fact, I'm going to draw it out how theoretically it would fill up, because this is what they mean by half filled as well. When you go like this, the first electron will go here, second electron wouldn't just go with that same shell, it would actually go to the next shell, third electron would go there, and this is what they mean by a half filled suborbital. And then because it has 4, the fourth electron would go in the negative spin in that same shell as well, like the beginning one. So sulfur, Okay. For its valence shell, the center is going to be everything like the nucleus plus its other shells. Okay, so we don't draw specifically because it's asking for valence shell. We do not draw the other shells there. Okay, and based on this, we have for representation, we have that that 3s2. Okay, then we have that one p shell that's has the two of them. Then we have those two s shells that are those two other p shells that are incomplete. So these are the valence shell representations of helium and sulfur. Let's see how we did. So helium is 1s2, so we have this. Okay, this works. In fact, I'll just label them helium, sulfur. And now for sulfur, oh, I see. So they'd still put every other shell, but they only ask for valence electrons. So I would actually say that you would not want to do this because it's only asking for its valence shell, as you can see based on which part we were highlighting. Okay, not the rest of it, because you can see they still have that 1s2, then they have the 2 s2 2p6, and then they have now the 3s2 3p4. But overall this would be incorrect. They only ask for valence shell. I'm only listing as incorrect because it's just important that you read and ask this question specifically for what they ask, so you don't trip yourself up. With that being said, I do believe that's all the questions that we can cover for today's time. So I just want to thank you again for joining me this evening. You have a lovely rest of your night, and if you're still looking for more help or just have any other questions, definitely check out the links in the description below. We're always here to help. And with that, I am signing off for the night.